Hello, this presentation is about investigation into strength and rheology of cemented paste fill using pozzolanic waste products and plasticizer as partial cement replacement. This research was done as part of master's by research in James Cook University. Now, cemented paste fill is basically tailings, mill tailings plus cement binder plus water, and some additives or admixtures are used added to improve the function of the paste fill. Now, paste fill basically for support in the excavation underground, especially filling up open voids, and provides safety. And because paste filling, it fills up a stove very quickly, it turns over the stoves very quickly, so it's an efficiency in the production. Most importantly is disposing the mill tailings, the waste, into the underground, which becomes environmentally friendly disposal system. Now, there's challenges and problems associated with cement paste fill, and basically it's to do with the expense involved in the application or usage of cement. Cement paste fill uses 3 to 7% cement binder, so around 10 to 20% of the original cost is basically cemented paste fill, and about 25% of the filling cost is around cement, is the application of cement binder. And because the paste fill has to travel longer distance, high water requirement, or the high water issues, so in turn, the more water, less cement, it basically prone to liquefaction. So any seismic event or a blast vibration can liquefy the paste fill. And also the production of cement uses a lot of energy. So calcination process from converting calcium carbonate to calcium oxide consumes a lot of energy. So for every ton of cement produced, around 800 kilograms of carbon dioxide is emitted. So in a way, the cost of cement actually, prompts the research into pozzolans trying to use something else to replace cement so that the cost of cement can be minimized, and also the production to be minimized so that less carbon dioxide is emitted to the atmosphere. So the objective of this research is basically to optimize paste filling, and that is by using pozzolans to replace cement and polycarboxylate plasticizer to improve the workability rheology of cement and paste fill to travel longer distance. Now, in the next couple of slides, we'll be discussing on the test methods, the results, and the discussion. So basically, the strength test, the microstructure study, and the rheology. Now, the materials used, it's the mild tailings is from George Fisher mine in Australia. The binder types, we have 5 binder types. The first one is 100% general Portland cement. Second one is 25% fly ash, 75% general Portland cement blend. Next, 60% slag, and 40% GPC blend, and 10% pitch stone, 90% GPC, and 20% pitch stone, and 80% GPC. So various solid contents, mostly the 74% solid content. Binder dosage varies from 3, 5, and 7, and then polycarboxylate dosage. Now, the formula on the other side basically gives the calculation of the requirement of the ingredients to be used. Yeah, the strength test, especially the universal comprehensive test. Molds of 50 millimeter diameter, 120 millimeter height were cast with paste fill, so it took you 7, 14, 28, 56, and 112 days. And then they were trimmed and loaded under the ECS machine at the rate of 1 to 2 millimeter per minute failure. Now, the results from the ECS tests from the 5 binders used at different dosages of 3, 5, and 7%. it indicates a general trend here. So you have a control mix 100% GPC right there. And then you have the piston blend with GPC 20% and 80%. And then you got slag here 60%, GPC 40%, and then fly ash 25%, 75% GPC, and then the 10% and 90% GPC. So looking at that, the 3% binder, it doesn't give you a result that is expected to be utilized underground. So the results, the strength that you will lower than 150 kPa, so they couldn't be used underground. However, the 5% and 7% binder indicated strength that can be applied in underground. So 5% cement, the strength varies from 200 to 0 kilopascals, and that can be used in where stopes, the paste field can stand up when stopes are mined adjacent. Now with the 7%, that was the highest strength achieved, so it can be used to serve as seal or crown pillar in underground. Strength activity index was also done to figure out, see which of the binders can be used, satisfy the ASTM standard 6C618. So looking at the graphs, the top 75% threshold is somewhere there. Most of the strength above the SAI, strength activity index threshold, and at the bottom as well, the graph, the strength activity index 75 somewhere here, and then you have the control mix, and comparing with the control mix, the rest of the blends, pozzolanic materials are above. So which means that these materials can be used in cement and backfilling. And they satisfy the ASTM C618 standard for pozzolanic materials. Microstructure analysis was also done for control mix and piston blend mix. So it was scanned at 7, 14, and 28 as accurate samples, and a general trend is basically entry guide formed at the earliest stage at 7 days, and then as the current days increases, more calcium silicate form. So the more calcium silicate form, the less the void, so it increases the strength of the material. Now, Rheologist test was done using a Brookfield rheometer for yield stress and slum cone for slum test. So with the effect of polycarboxylate on yield stress, it was generally observed that as polycarboxylate dosage increased, the yield stress also reduces. Reduces when the polycarboxylate dosage increases, the yield stress reduces. So looking at that one, as at different binder dosage 3, 5, and 7, at the 0 polycarboxylate dosage, it's higher than maybe 6% polycarboxylate dosage, which is lower. So the polycarboxylate dosage was calculated from the binder dosage. So generally, the more dosage of polycarboxylate, the yield stress reduces. Effect of polycarboxylate on the slum. So different solid content, 74, 75, 76, 77 were used, and at different doses of polycarboxylate. And can be seen as the polycarboxylate doses increased, the slum also increased, and reduces the low 0 or 4% polycarboxylate doses. So in a way, polycarboxylate helps increases the slum of the mix and also reduces the yield stress of the mix. And the yield stress and UCS were also plotted to figure out the optimal mixes, and most of the optimal mix with more than 1 MPa and less than 150 pascals yield stress, they all fall around here. So most of these mixes here are 7% find a dosage. So in conclusion, the strength results indicated blends of SEMs used attain strength activities above the threshold of 75 compared to contrast. The pozzolans that were used complied with the ASTM C6, 18 for pozzolans to be used in concrete or paste filling. Interestingly, the piston pipe, which is a volcanic rock, has never been tried before in magma filling, but in this study it indicates that it is comparable to the results of the other pozzolans, the fly ash slag, and also the cement. Now, one of those 3%, 74 solid coils, the strength was low, 150 kPa, so it poses a risk of liquefaction and cannot be used underground in paste filling. One of those of 5%, 74% solid coil that after 28 days curing is 200 to 600 kPa and can stand up and can be used in underground stope filling. Dosage of 7% at 74% solid contents ECS for majority of the weeks after 28 days, reaching 1 MPa and can serve as pillar or support in underground. So polycarbonate also improve the workability of the paste fill by increasing the slab and reducing the yield stress. Overall, the use of supplementary materials can reduce backfilling cost, and by replacing cement, reduce the cost of backfilling. And the use of plasticizer can reduce water requirement and improve workability for paste fill to travel longer distance underground. And moreover, disposing of waste mill tailings into underground waste can minimize surface footprint and make backfilling more environmentally friendly. So any toxic material in the paste filling can backfill or dispose back into the underground instead of affecting the environment. Thank you, everyone. That's the end of the presentation.